Anyways, thank you very much for joining us today. My name is Dr. Jerry Smith. I'll be one of your two hosts this afternoon. Let me see if I can get my stuff going here. That's who I am. And my colleague Arnie, he'll be on in just a few minutes. He's going to help you walk through some stuff that we need to do before we actually do our work today. My doctorate is in computer science. My specialty is in AI. I laugh a lot when I say that, because I'm one of the few people, I guess, that actually gets paid for the PhD in the world. And my subspecialty is in evolutionary computing. The use of one of two techniques, both evolutionary population-based intelligence and artificial life, which is the intelligence of many things, emergent phenomena, are two areas that I really enjoy working in quite a bit. Today, we're going to be going through this agenda over the next 2.5 hours or so. That's a long time, right? So I will warn you ahead of time that time can go quickly, and it can also drag on quite a bit, right? What you're going to get a chance to do today is get some hands-on practical work. If you choose not to do it, there'll be a recorded session available to you after this. You'll also be able to do take the files and do them on your own down the road. So if all you want to do is watch as we go through, great. If not, you can spin up the work and work along with us. So today we're going to set up the lab. We're going to get that going, because that takes a little bit of time for the gears to grind through and get everything up and running in the cloud. During that time, I'm going to talk a little bit about artificial intelligence and perspective. It's our point of view on AI, and hopefully it will become your point of view as well, although not required. We're then going to walk through and do a walkthrough of the process. So you see everything at once, about 30 minutes of a walkthrough. We're going to do something in breast cancer. We're going to take a look at fine needle aspiration. It's a classic classifier approach, but we're going to use causality to model that, along with creating a brand new model. Last time we were on and we did this, we made a little science news on that. I'm hoping to make some more science news today. After that, you are going to get your hands wet into the science of causality, where you're going to get a chance to take a look at student grades. We have data from a research project that studied studied student grades over a period of 3 terms. And we're going to get a chance to see what are causal drivers for student grades. And I think you're going to actually be surprised about some of the outcomes of that. We'll get more into that a little bit later on. After that, we're going to go into and do machine learning. So we'll go into Azure, the ML space, and you'll actually be able to code up taking those causal inputs and creating a causal-based predictor. And a causal-based predictor, as you're going to learn a little bit later on, is called a digital surrogate. Accenture and Gartner believe that over the next 3 years, digital surrogates are going to be the capability, the set of technologies that are going to have the most impact on the world as we know it. After that, we're going to have a discussion on optimization, and then we're going to have some closing remarks, and then you guys will be off on your own. And we'll talk more from that. All right, so if I move on here, what we're going to do now is we're going to set up a lab. Here in front of you is the steps that you're going to go through. I'm going to introduce you now to Arnie, and Arnie's going to walk you through how to take, oh, by the way, if you see me start pointing over here, it's because I have 2 monitors. You're going to walk you through the event, how to click on the link, how to activate, launch the lab, get the environment up and running, grab your username and password, do all that sort of stuff, and get you going. And then I will rejoin you for about another 30, 40 minutes after that. So Arnie, I'm going to send it over to you.
All right. Thank you, Dr. Jerry. And again, if you want to tell them the disclaimer that this is being recorded.
Yeah, we are being recorded. And I love seeing myself on your screen.
Just getting it set up here, sending it live.
There we go.
All right. So here we go. So when you click on the link that Dr. Jerry showed on the page there, you sign up. There's going to be some form you fill out, put your name, well, not address, just your name, who you work for, email address, and so forth. Then you click submit, and you'll be routed to this area here once you launch the lab. So this is our lab environment. We're not going to use any of these virtual machine that has been set up. We're going to go over to the environment details. And here's where we have all the Azure information that we need. So most importantly, we just need the username and password. So what we want to do is to click on a new tab, go to portal.azure.com. And then since I've already done this, you would just go in here, copy your username, click on that, and then go into your Azure portal. So for those who are not familiar with the Azure portal, this is kind of like the landing page. And so this has been set up now with all the resources that we need for this lab. So let's go ahead and click on all resources. And then we're going to look for the machine learning services. So that's this one here. Click on that one. And then we'll launch the studio. And this is the kind of data science, their studio or the portal. You have to kind of click on the account again. Letting this load up. So here we are in the data science portal. So in here we have 3 types of kind of data science ML environments. We can create a notebook, AutoML, and we can use a designer. Then we got some assets, set of pipelines, experiments, there's some data sets. But for the time being, let's go ahead and jump over to the compute. So we already have set up a compute cluster. So we'll use this compute cluster when we do our ML prediction model. But for the time being, what we need to set up now is to have an instance compute, and that is to run our notebooks. So we're going to rely on notebooks in this session. So go ahead and select the compute that you want. You can pick whatever you want. Doesn't really matter for our case here. It's not that compute heavy. Give it a name. And then this is going to go and set up the compute. In the meantime, let's jump over to our notebooks. And let's upload some files into our into a folder here. So let's go ahead and add files and upload files. And I should have them ready here. So I'm going to upload these 3 files. So this should have already been sent to you in an email. So now we have uploaded those files here. We need to upload some folder as well. So click on the add files, upload folder, go to the same area, and we're going to upload the figures. So this is just to kind of render our notebook nicely. And then we need the data sets. There you go. And then so for our last setup item, before we jump back to with Dr. Jerry, well, we might have to wait a little bit since the compute resources are still running. Let me double check here. Yeah, it's still being created. So while we wait on the compute to run, I'll give it back to Dr. Jerry, and then
Awesome.
we'll have to go back in here, and we have to install some files when we get a small break again. So I'll give it back to you, Dr. Jerry.
All right, let me do this, send live. It's always fun playing in this space here. Let me just get me over there because I was complaining that I don't like to see my face when Arnie's slides are up. All right, so here we are. We're back again. So couple things. One is this is AI in a Day, sponsored with Microsoft, right? And so one of the things that we like to point out is, I'm a practicing data scientist, is how easy it is to get our ecosystems up and running, right? It's an amazing world, and for those who weren't around maybe 20 years ago, what we just saw was like the dark art, right? 20 years ago, you'd never be able to do that. Spin up an environment, get everything going, moving forward. And having an ability to do that with a partner like Microsoft is just an amazing phenomenon. All right, so we're working through this. Let me just move forward here. All right, so let me spend a little bit of time on AI, right? So this is a few slides. This is not a slide-intensive presentation. And by the way, you'll have all of you will have access to these slides. So if there's anything in here you like, feel free to go ahead and use it. The purpose of this is just setting a stage on why we're here, right? And as you begin to think about the global presence of AI in this year and next year, we're looking at about a $4 trillion industry, which is going to affect us all. But how does that really break down, right? If you think about $4 trillion being applied, what does that mean? Where are we making those investments? Decision support, virtual agents, decision automation, smart products, all are interesting places to go. But the most important piece out of all this is, as we look over the last 3 years, and we begin to take a look at how companies are looking to deploy these things, we see that we move from an area where we're thinking about AI as deep neural networks to an area this year, next year, where companies are turning to use this capability to draw new revenue, new margin, and also to help in the engagement of non-routine tasks within an organization, right? So we've gone from thinking about AI as a science experiment. Hey, what kind of deep neural networks can I do? Hey, how can I modernize my analytics platform? Hey, what kind of new ways can I use this to monitor, to a situation now where companies are saying, enough of the science experiments. Let's get on with making money and getting rid of boring tasks for people, right? Which improves retention, reduces turnover time, increases margin. So we're talking revenue and margin now, which is pretty exciting. If you're not in the AI space, right? If your company's not, this is a dire warning, right? AI is what we would consider a non-linear, asymmetrical capability. And what does that mean? Let's break that down. Well, first of all, AI is non-linear, and that is the more knowledge you get, the more knowledge you apply back to those processes, the more knowledge you gain. That is a nonlinear exponential growth function. That's powerful. Second thing is it's asymmetrical. And what we mean by that is, if I apply it first and you don't apply it to counter whatever I'm doing, the gap between us increases immensely. And it could actually increase to the point where the competitive advantage one has with AI is so far down the road that it is practically impossible for a company who's just now starting in AI to ever catch up. And that's what this is showing here on the very far left-hand side, is over the next several years, companies that are first movers in this category will have a demonstrable impact on their ability to compete in the marketplace, right? So you just need to think about that. It's an asymmetrical, nonlinear threat to your company. If you don't do it and somebody does it to you, it could be game lights out for, or what we call an extinction level event for a company. Well, enough of the gloom and doom. All right, so let's get into the way we look at this, what we call the cycle of life. There's going to be two slides that I'm going to talk heavily on, and then we're going to move on. This is the first one. This talks about the cycle of how we do things, and the next slide is going to talk about capabilities. The cycle starts off, it's a simple 6-phase cycle. Now you would think, as you're turning to your email right now, you think, well, that's pretty straightforward, but it's really subtle in many ways. If you think about starting off at the very first, where we collect data, one of the questions I ask anytime I'm engaged with customers is, what is data? Right? Now you can read the slide and see what it is, If I were to ask you the question, if you were to really sort of take a deep thought about this, what is data? Well, data is the debris of human activity, right? It's because of us, not in spite of us, as I always say, right? So it is the debris of our work. Now, I know there are going to be some people out there saying, well, is it debris or is it a product? It is the stuff that comes from you and I doing things in this process, right? All of that data is often collected in a company, but not all of it is important to business outcomes, right? Some data we collect because of regulatory, some data we do because we need it for transactional activities, but not all data leads to a demonstrable change or improvement in a business goal. That's why we moved to step 2 in this process. Step 2 is thinking about all of our data from a causality perspective. And that's the very first activity we're going to do today. We're going to take a whole bunch of that data, in the case of fine needle aspiration, or in the case of studies around education. We're going to figure out of all that data, what is causal to a business concern? What causes our ability to predict breast cancer? What causes grades to improve? Not what is correlated, but what's causal. And there's a difference. And I think we've all heard of the differences. I often sort of use the analogy of a surfer, right? A surfer doesn't cause the wave. You know, given a lot of training and a great board, he can ride a correlated wave to the shore and do some amazing things. But if the surfer really wanted to create a better wave, there's other things he would have to do to take advantage of that wave, right? Seed the clouds and stuff like that in order to make bigger waves occur over time. So the very first thing we do is we do causal. Now, once we have a causal input, what do we do next? Well, we build predictors, right? I mean, that's half of our life. What kind of predictors? Well, predictors that are based on the causal inputs, right? The things that we control. Remember, causality is we can control them. If I vary those things, if I force function that variable to change, the output will change accordingly, right? I have control over those things. So we call those a very special kind of predictor. That's a digital surrogate. That's the new word that's going to go ping over the next couple of years. Gartner, Accenture, folks like that are predicting it to be the technology of choice, whether you're building a digital surrogate of a pump or a car or a spaceship, or a digital surrogate of a customer, or a digital surrogate of an employee. These are all synthetic representations that now that you know the control inputs, you can predict how that thing's going to respond. With that in hand, now that I have a digital surrogate, causal inputs, predictive outputs, I can then move into the last phase, which is prescriptions. How do I maximize my output as a function of inputs? And if you think about it, we'll get into this a little later on, that's a giant search, right? That's a Monte Carlo search, that's a particle swarm optimization, that's evolutionary computing, blah, 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 a lot of different stuff in there. But once we have that mapped input to the maximized output, we then do what? We take those prescriptions, we go into the field, remember they're causal, we go into the field and we do what with them? We implement them, right? We actually sit down at the fish farm and implement these things. We actually go into the store and we implement them in terms of the refrigeration systems. We actually go to the bank and we implement these as fraud prevention characteristics. And then what do? We wait. We wait for a minute, an hour, a day, a week, a month, a quarter, a half year, etc. For what? For those activities to change the behaviors of people, and for those people's behaviors then to be picked up by the systems that we are have designed to detect that data and store that data. Then we wash, rinse, and repeat, right? And when you wash, rinse, and repeat that cycle, an amazing thing happens. You actually change the performance of your business and you bend your business curve. You cannot not bend your business curve if you apply this process. You have to change. And that's a whole separate set of conversations around systems engineering and systems theory we won't get into today. It is the lost art of software engineering, but it's something that we could look at later on if you choose to, if you think that that's a good thing for us to focus on. Anyways, so this is the process we like to employ. Oops, wrong way. Oops. Here we go, right way. Wrong person. All right. So the next diagram, this is the capabilities model. Now so the first one was on methodology, which is the cycle. How do we move through this? If you structure your engineering programs around that, you will change your company, right? The next question is what do you do in those areas? What are the things that we do when we say things like causality, or we're going to go and develop a predictor, or we're going to develop a prescriptor? Well, this is data insights. It's a capabilities model. I think we're all familiar with capability models in general. This is very specific. This translates the data on the left-hand side, which is your enterprise IT and open source. Enterprise data, that's the data about your customers. IT is the data about the transactions they have interacting with your websites, et cetera, your Internet of Things stuff. And then open source data, that's all the third-party data that's external. Think of it as social determinants of health, if you're in healthcare or in banking, as an example. From there, we then translate that data. We bring it in, we harvest it, we manage metadata around it. We do a whole bunch of activities in the center under information, whether it's taking a look at topic extraction or temporal time analysis or spatial analysis, et cetera. We then move into doing stuff with that, whether it's sentiment. We then apply things like genetic algorithms or deep neural networks for feature extractions, and then we aggregate them into an AI insights engine, and then we present those actions back to the customer, right? And then what this also shows is it is ability to identify who does the work, right? Oftentimes I often hear from customers that, well, we need a data scientist. Well, not all data scientists are the same. The ones on the far left-hand side are more engaged in data engineering and cleaning activities, and the ones on the far right-hand side are more engaged with insights extraction. And those two kind of data scientists are very different. There's also different levels. There's junior people and then there's senior people. So this diagram tends to show that, along with the kind of platforms they work on. So that and $1.25, we still don't have enough money for a cup of coffee. So let's go ahead and take a look at how we're going to apply that today, right? So today, we're going to go off and we're going to grab data from UCI's data repository. If you are somebody who's looking for data to work with, to test proof of concept, your machine learning ideas, it's a great location, right? Great location to do work in, because it's a lot of free data. We're grabbing two sources. We're going to grab the fine needle aspiration, FNA data for breast cancer. We're also going to grab the education stuff. We're going to bring that in. We're doing text harvesting, pretty straightforward stuff. You'll see Arnie do that, and you'll do it. From there, we're going to do causality, which is the very first thing we're doing right there in the center. So we're going to figure out, of all the data, what's causal. That, to me, is the coolest spot of everything, because it opens your eyes. After that, we're going to go in and do some descriptive analysis, right? We're going to do some classification work, some decision tree stuff, and build some models and go off and do some work. So you're going to get a chance to do all of this today. And we're going to do this in this ecosystem. Oh, and one last thing. If you take a look at this, as soon as it goes back here, you'll see that we're going to do this with on the very far ecosystem, and we're going to do this data science and data engineering stuff, right? So that's how we map those things out. So how are we going to do this? Well, we're going to do this in Azure. These are the components. We're going to use Jupyter. We're going to do some side learning stuff. We're going to get into machine learning. It's all going to be CPU based, no GPU stuff today. And then in here, we're going to, based on notebooks, grab some data sets, which you've already started spinning up. We're doing some training activities, compute, and then, again, CPU stuff. And then lastly, we're going to get into actually building out, visually building out some very interesting machine learning components with Microsoft's Machine Learning Visual Designer Studio, which I think is pretty cool. Because again, as a data scientist, I don't want to worry about all that other stuff. I just want to get in and do my particular work, right? So with that said, I'm going to turn this back over to Arnie, who's going to finish up on the lab stuff. And then we're going to actually walk through this exercise. Yep. He's going to walk through the breast cancer, finite needle aspiration. He and I will banter back and forth to this, but right now I'm going to turn it back to him, and he's going to get that other stuff up, and then we're going to start with the walkthrough.
Thank you, Dr. Jerry. So let me go and share my screen, get the content in. All right. So now that we have the compute running, so again, we got instance, compute cluster, an inference cluster, and
oh, by the way, real quick, real quick.
Yep.
The brain is still going here. If you have questions, if anybody has questions, please post them. We'll get better. I just noticed that, somebody asked, will we get a recording of the session later on? Absolutely, we'll get that. But if you have questions, just pop them in there. We'll do the best we can to get back and forth. We have the questions up and running, and we'll try to make it more interactive than what we currently have right now.
And then, so going back to the compute area, the compute instance is what is going to run our Jupyter notebooks. It can also do an RStudio and then terminal. So now that we know that it's running, so we jump back to the notebooks. And before Dr. Jerry can talk a little bit more about the breast cancer dataset, we're going to start by installing some necessary libraries. So let's go ahead and work in the Jupyter Lab. So that's kind of my environment of choice. You're welcome to work in the Azure notebooks or in the regular Jupyter notebook. Just hang on a minute for this to set up. So now we got our Jupyter Lab up and running. We have our the demo notebook open. So the first thing we need to do, and we only need to do this for one time. As if you install a library, a Python library on a cluster, you don't have to reinstall it or until that cluster has been removed or deactivated. So we're gonna uncomment these, and this is gonna go into the, using the exclamation point is gonna tell the Jupyter notebook to use the terminal underlying the notebook. So it's gonna go into the Linux terminal and it's gonna run pip command. So it's gonna tell the pip to install these two libraries. And this might take a minute or two. So Causal Next is our main causal analysis tool that we're going to run through in this demonstration. And then PyCharts is a visualization library we're going to use to visualize those causal drivers and also relationships. So Dr. Jerry, while we're waiting on this, if you want to go back and talk more through the breast cancer data set, what we're going to be looking at.
Yeah, of course I would. As soon as I can find where my my mouse went on me. There we go. All right, so I'm going to share. Let me bring this back up again. Share this piece and share that. And then send live. Just trying to see why my face is in here. There we go. There we go. Now we got it. All right. So a little bit about this first piece that Arnie's going to walk through. This is a study that was done on, as you see over here on the far side over here, that was done on 569 instances where they biopsied cancer cells. And one of the traditional ways is you biopsy the cell, you bring it under a microscope, you then do a series of measurements, 31, 32 measurements, and with those measurements, that can help a clinician make a determination whether or not the cells are cancerous or not. This data set is used a lot in testing classification algorithms. No new science there. I mean, this data set has been around since 1995, and you can download it yourself and take a look at it. Key thing is we measure certain parameters, 31 parameters in total around this, and then from there we can make determinations. So you download the data set, you have all the 31 parameters, 32nd field is it malignant or benign, and we can make this. What we're doing today, that's nothing new. What we're gonna look at though is what's the causal characteristics? Is there anything in that field that is causal to the actual determination? Or are they all causal? Are any of those measurements causal to it, or any of those measurements causal to those measurements that are causal, right? So we're going to begin to see that work. So what Arnie's going to walk us through now is a quick demonstration of that. We're going to determine the causality very quickly. We're going to bring the data in, and then from there, we're going to go off and build a quick predictor model on it, right? So Arnie, can you walk us through that real quick?
Yep.
And then you're going to go back, as Arnie's taken over the presentation, you're going to go back and then do this on the student data yourself.
All right, and we're live again here. We're still installing some of these libraries, so let's give it a minute here.
So we get to do a song and dance show. So let's talk a little bit about causality then, while we're waiting for this thing to spin up. Most data scientists, machine learning, and AI folks spend their life on the predictive and prescriptive work, right? Very little is actually done on causality. So one of the books that we recommend is The Book of Why. So if you take a look, I'll go to Amazon and type in The Book of Why by Judea Pearl. The Book of Why gives a clear and compelling case for why causality is important, right? He is, and I don't think he'd like me saying this, but he's the godfather, right? He's the great-grandparent of causality. He's the one that, let me know, Arnie, when you're ready.
Yep.
He is the one person that has laid out the case on causality. He starts off in the causal world by taking a look at some of the early studies around smoking and cancer. It is very hard to believe at one point 20, 30 years ago, we actually debated whether or not there was a causal link between smoking cigarettes and lung cancer. Hard to believe that was the case. And I remember it when I was a kid, listening to these debates and listening to the evidence at hand. And if it wasn't for his work, we would probably still be debating that area. But we now have an ability to determine through capabilities like mutual information theory, to calculus, to be able to create very rich. And how are we doing?
We're still trying to run through it. What I can do is I can also upload a file that we're going to use for the prediction piece.
Yep.
So while this, let me just go ahead and
show the group on how to do that.
Yeah, let me just go ahead and refresh just in case here.
This is the wonderful world of doing real-time stuff, right? No matter how many times you do it, there's always something unique that pops up.
Okay, let's just, so this one finished.
Okay.
This one was not completed. So it never kicked off. So I don't know, maybe that's why, oh, it seems to be finished. So there's just some glitch here. Let's go ahead and, so keep in mind, once you install libraries, you need to restart the kernel.
There you go.
So let's go ahead and do that. All right, so now that this is done.
And for those who don't know, restarting the kernel allows the kernel to then have access to those libraries. It's not a dynamic, I don't think they do dynamic kernel, dynamic library allocation within a kernel. So it's all static work, static pointers.
So as you can see here, we have some libraries that we need to import. So we installed the Causal Next, so we need Causal Next for sure. We now, have some.
Real quick, Causal Next is one of several tools one can use to do causality. In a different 45-minute lecture, we're going to introduce the group to something, a partner called Compellon, which has another approach to it. This happens to, and that is a paid-for approach. This happens to be an open source tool, which you can download free and use it in your work. It's a little tougher to use, requires a little bit more technical skills, but at the end of the day, it provides you with a slightly different perspective on causality, but it's open source, hence free, unquote.
Yep. Yeah, we have some Causal Next libraries. We have the pie charts library that we install for visualizing our or graph. We have some network X, which is also helps with visualizing the graphs and compute some of those kind of stabilizing our graph. But let's go ahead and jump into here. So let's set up some parameters. So this, for those who are not familiar with pandas, pandas is our data frame kind of library for data scientists in Python. And by default, I think it only is going to visualize 10 columns. So we want to increase this. So you can put whatever value in here, but for our case, we're not going to go over 60 columns. So that's what we need to set up here. We need to, for our pie charts, we need to load JavaScript. So we need to have that. And then we're going to just declare an empty data frame that we're going to use in here. So let's go ahead and look at the data we have. So we're going to look at breast cancer. So here's the data we have. We have, like Dr. Jerry talked about, there's a biopsy done, and they will measure the sample, the tumor sample, and these are some of the parameters that they measure from the biopsy. And again, we have a machine learning record. That's what we call a data set when you have a patient per row, in this case, and then you have columns for the features. And then we have our target column as being the diagnosis. What is important, in at least for this data set here, is that we want to eliminate a column, just this one column here, the ID column. And normally you don't want to remove any columns that could be of importance for the causality, but we know for a fact that there is no causal relationship between ID and these patients. So any kind of random ID stuff could actually block the causality from maybe seeing a causal relationship. So we want to remove this ID column from our data set. So let's go ahead and drop the ID column. Then the next step is to transform our data set. So our data set here is almost all numerical or continuous variable, meaning it's a number that is continuous and not a categorical like the diagnosis. But in other data sets, there's, in many cases, we're going to have categorical values, and Causal Next will not accept any non-numerical values. So we have to convert everything to continuous variables or numeric. So that's what we're going to do. We're going to convert the diagnosis column to 0 and 1. So we do that here. We're going to rely on some scikit-learn label encoder for easiness. And then we see the results here. So we removed the ID column, and then we converted the diagnosis for being 1 for being malignant and 0 for being benign, as you can see here.
Yep.
Then the next step is to break up our data set into a target and features. So we go ahead and do that. We select our target column here, which is our diagnosis. So that's our target. So this is similar to what we do in machine learning for when we're creating classifiers. We select the target, and then the rest is going to be in the features. So for those who are familiar with that process, then we have to set up some configuration for our causal next, and we're going to fit the model. So we're going to fit our features with our target and try to create, going back, there are two-part process to causal analysis. The first piece is to figure out a graph that is going to determine a causal relationship between every feature. So that's creating the graph. the second piece is to apply conditional probability on top of the graph that we can then use for kind of figuring out and do some certain things like do calculus and just seeing the probability of if we apply if we increase population on one area, how that'll affect our target, for example.
Yeah. So let's do that.
Yep. So let's give this a minute. I keep forgetting that maybe I should pick a more powerful compute for this session. I keep comparing to my laptop.
You mean that quantum machine that you have as a laptop sitting on your desk? Oh, look at that. That's pretty.
Yeah.
There, I can see the causal relationship there now.
So let's do this a minute. Let this balance out. So this is where.
So what this did was it grabbed all that data and it used theories like mutual information theory to figure out the entropic relationship, the entropy in the information, and then create a relationship. And then it uses a graphing function. There are several different types out there. I forget which one we're using today. I should know that off the top of my head, to graph the relationship in there. And you can see lots of relationships. All of it, this is very non-meaningful to us today. So what do we do with this, Arnie, to make this more meaningful?
Yeah, so we will have to apply this function here, remove edges below a threshold. So we have to apply a threshold to our graph here. So initially,
in theory, everything is somehow related to everything, right? This is not a perfect causality world where it's not binary. There is, at some level, there's a 0.001% chance of something being causal related. So we're just removing those elements that are less interesting to us. And this is a little bit of the art that comes in.
So we do that, and let's plot it again. So now let's take a look at some more meaningful graphs.
Now we're having some fun.
So let's find our target, and we have our target here.
That's the diagnosis. That's the malignancy diagnosis. So if we hover on that, then we can see of all the parameters that goes into classical modeling of fine needle aspiration diagnosis, or breast cancer through fine needle aspiration clinical work, we find out that there's 4 components that are causal. The other components are related to those components, right? So again, we're not making any new news here when it comes to the science of this, but what we are showing is that of all the parameters we have, here's how they're all interrelated, and that there are 4 actual parameters that lead to a better understanding of that causal work.
And then another thing to look at for the graph here. So we've plotted now our graphical representation of our kind of the mutual information theory, how it figures out what is causal to each other. And we also have an arrow that tells us that this is causal to that. And then we also have the thickness. So in our graph here, we see that, for example, this parameter mean has much thicker curve to the compactness mean than the rest of the arrows. And this just means that this is has more higher influence than the rest of the curves.
Okay. So what should we do with all this?
So now that we've got this graph here, we need to remove some of the extra parameters or extra features out here that don't seem to have a causal relation as a strong causal relationship. Again, we applied some threshold, and that removed a really weak causal relationships out. And what we can't have is a 2-part. We just have to have one continuous causal relationship. So we need to kind of remove some of these things. For this exercise, we're just going to take a look at our 4 features here. So we're just going to go and take out what are actually the first causal pieces to the diagnosis. So we do that with this command here using the predict, and then it is going to pull out those 4 features that are causal to the diagnosis. So we just do that, get the column list, and then we will apply some, get the target list. We create a new structure out of that, and I'll show you again how it looks in the end here. So now we have recreated our feature table that we had before with only the features that are causal to the diagnosis. And so we also applied here a Bayesian network. So this is where the starting point of where we're going to apply a conditional probability to our structure. So there's a Bayesian network. We've already given it our structure that we already calculated, and we tell the Bayesian network, here's the structure we're going to work with, and then we start working with the features that we have there. So when we use a conditional probability, we have to compute conditional probability between all the different variables within each column. So it is very important to discretize our features. What I mean by that is that we want to take continuous variables and we try to bin them up. This is what we call discretize, is to bin them up into some meaningful kind of limits or parts. And that is we do that to simplify the computation. And otherwise we'd be all day running this model, or it would probably blow up using too much memory. So what we need to do is I kind of created a simple example here of bin up all these features here, and then I'll show you the example here after this. So now we can see that I've taken the continuous variables here. So the radius, standard error, area standard error, and it just looks at minimum value and the maximum and tries to put them into a group of low 1, or level 1, level 2, level 3, level 4, and so forth, and just categorize the values into those bins. So now that we have the features back in here, we will train the conditional probability on the structure. So the Bayesian network already knows the structure, the conditional, that knows the computed causal structure, but now it's going to go and try to fit the features to that model. So we do that. We have already computed now the conditional probabilities, and then we can view the probabilities. So here's an example of how we look at the conditional probabilities, but this is of no interest. We want to look at the diagnosis. So let's go and view that. And here we can see the conditional probabilities between all the features and the target.
Which is interesting. And remember, this is just a quick walkthrough. So why don't we move into the modeling world now, where we actually take our causal inputs to the diagnosis and then compute a new predictor or a digital surrogate from that.
Excellent. All right. So now that we've done this, let's go back into the Azure Machine Learning Studio. Let's go ahead and upload a data set. So this is we could have exported it out and put it in here, but let's go ahead and just run this small exercise here of getting our data set in here. So this is our breast cancer data set. It's a tabular one. And we're going to put it into our default Azure blob storage. Here's our breast cancer data set. We're going to upload it. So it's going to parse the data set, try to apply a schema to it. It is delimited. We have header. So let's get a preview of it. This seems to look pretty good. So we're going to accept that. We will accept the schema as is. And let's go and create this file. So what this allows us to do is that once we create a data set within our data science platform, is that it makes it super easy to share between all the tools we have, the notebooks, AutoML, and Designer. So it just gives an easy way to kind of view the data set anywhere. So it's a good practice to get your data set that you're working with, to get it into the data set here. So let's go ahead and kick off the Designer here. So for those who are not familiar with the Designer, it's a graphical it's a graphical representation of creating machine learning models. And it's done in a really nice way of just kind of plug and play. So initially we saw that we had already a compute cluster set up. So we're gonna select that one here. So this is our default cluster. And now you can see here that our data set that we just created, the breast cancer one, is already in place here. So that's why it's important to bring it into the data set here. And now it's visible throughout our tools. So let's go ahead and drag our breast cancer data set in here. And
I just love drag and drop as a data scientist. I can't tell you the ease of how easy it is in a life when you're focusing on the problem domain and not the IT domain, right? So for you hardcore data scientists that are out there thinking there's nothing like Python scripts, I'm talking to my Arnie friend here, getting in and doing visual representation as cognitive, just a little sidebar, as a cognitive psychologist, visual representing problems is one of the most productive creative activity you can do. And so anytime you can get out of textual world into visual world, it's good for the problem.
Yeah, and really it will take you probably a good few years to be really comfortable with Python or being efficient with it. But this is a 1 week of trial and error, and you're pretty good at using this platform. So you're gonna get to the results a lot faster.
And so let's just pause for a second as a data scientist, right? So I mean that's what half of us are here. So we take a look at this, we can automatically begin to see what? We can see different kinds of distributions that we have available. Some look a little Poissonous, some look a little normalish. As we scroll from left to right, what other, oh, look at that. Yeah, there we go. Nice little exponential. So, and in here, we're able to get a sense of how our data is distributed and what would that tell us in terms of the kind of modeling that we would need to have in going forward. So cool stuff here.
And so this is available, like you can always view the data set you import. You just have to right click on it and you can visualize the data. And you can also, as you go through each step here, processing step, you can then view the results of after each processing step that you've already run. So before I assemble the whole data set, what we're going to do is to take the data set we just worked with. We had the target, the diagnosis, tumor being classified as benign or malignant, and we're going to separate that out. We're going to remove our ID column. We're going to split our data set into test and train, probably split it 30-70%. We're going to apply a machine learning classifier, probably a boosted decision tree for simplicity. And then we're going to compare or score the model and comparing the trained aspect of the data and then also the validation data or the test data. So let's go ahead and get started. So we have the data right now, and now the next step is to select columns. So we do that to select column in dataset. So we do that because we already had, we'll have an issue with our ID column here. And also what we ended up with, so we want to build a digital surrogate. So going back to our model here, we ended up with only these features here. These are the causal features to our to this target. So we only want to work with that. We don't want to work with all the features. So we're going to have to go and select those features.
And again, the digital surrogate is a causal AI model, right? Digital surrogate is these causal inputs, which means as we control them, which we can because they're causal, we'll be able to change the output, right? Going back to the server, right? The server, this isn't correlation. This isn't him that person taking advantage of a wave. This is that person creating a higher wave. And that's what we want to get to. There's a saying that I like to bring out usually about now is that I like to believe that I'm about changing the future, not just observing it, right? My goal in life is to change tomorrow, not just observe it. I have a crystal ball on my desk, which allows me to predict things, but the real goal in life is to change things. And that's what we're trying to get through here with this causal-based digital surrogate. Back to you.
Got it. So now that we selected the target and then the causal features, we go ahead and split the data. So again, we have, I'm selecting everything. All right. So now we just we're just selecting the columns. We still have all the data, all the rows. So the select columns is going to pull out the columns you need. The split data is going to look at the row wise and split out rows that you want to use. So in here, let's go and select here, and we can split at a row level. We can apply regular expressions, or we can just do a regular split. So we want to do 70-30 for simplicity. There's also some other features here we can stratify it. So if we had sensitive data set that are uneven, for example, which is a lot of cases with healthcare data, is that you have very limited amount of patients, and a lot of times you have to use stratified. So meaning that you will have to make sure you keep the same distribution of malignant and benign patients in both the training set and then the test set. So then you would turn on the stratified split. So then you just to put it here true, and then you select the column being diagnosis. But for simplicity, we're just going to work with non-stratified data here. But we're going to split the data. 70% are going to go out of here. 30% are going to go out of here. Then the next, we need to train the models. So let me go just kind of jump out of here. We'll look at all the stuff we can do here. So let's go ahead and bring in train model. Bring that in here. We want to make sure we select the target. Since it's not connected, it's not going to show us anything. So let's go ahead and do that. Let's try that again. Still not allowing us to do that. That's okay. Let's apply the classification algorithm. So we have several regression algorithms. So regression is for classifying kind of continuous variables when you're trying to predict maybe a value that you want to get an output. And then we have some clustering here, and then we will go into the classification. And the classification, we want to do binary, because we're only working with benign or malignant. So 2-class boosted decision tree. The reason I'm picking boosted decision tree is that it is kind of bulletproof. It's quite performant. It's a really good model, and you don't have to worry so much about our scaling or normalization of our data sets. You can even work with categorical values as well as numerical values. So that's the benefit of having the trees modeling. So we don't have to play with any of the parameters, but you're welcome to change those here. So now that we have this in place, we can go ahead and select our target. So now that we have that running, let's click the diagnosis. So now our trained model cell here knows that when you train this model, it's gonna use the classification, try to classify the model using diagnosis as the target. And it's gonna train on 70% of the data. So let's go, the next step is to score our model. If I can get the right area here, let's go and score the model. So we do the scoring to just apply. So the model will try to predict these features, apply really well with this target, and then once we get the output from that and we apply the inference modeling, the model is gonna give you a prediction and probability. So the score model is gonna take the features or the whole data set, and it's gonna apply the inference and record your probability and your labels. So that's what we're gonna take here. So we take the trained model and we take a feature set that we're gonna apply to it. We also want to compare the training set with our test set. So why do we do that? We want to compare how well our model got trained. And we can see clearly if the model is over fitted and if we should trust it or not. And then the last step is to evaluate the model. And we're gonna take each step here and compare them. And so evaluate model step is just to make it really simple for us of plotting and give us all the necessary data that we need to kind of check the quality of our modeling and the results. So that's the last step here. So overall, we took the data, we took out or only used the columns that we needed, the causal features. We split the data at a row level 70%, 30%. We applied a prediction model. We will train the models and we'll score each data set separately. And then eventually we'll combine the both, or bring in both models or the results, and we will plot them up in a nice way. So let's go ahead and submit this. So we've not created an experiment, so experiment 1, submit. So that's how easy it is to create a prediction model in Azure Machine Learning Designer. Really simple, took us, I don't know, a few minutes, me talking overly much. But while we're waiting on this to run, should we talk about our next?
Yes, yeah, let's get back. Let's get back. This is going to take a while to do its compute cycle on and produce some results. So let's now move into us doing less talking and you doing actually more work. So let me go ahead and share my screen back again and grab this, grab that. Where are we? This guy. Come on. There we go. Share that. And then send live.
And if there's any questions from the audience, please submit them and we'll try to answer those as we go.
Yeah, I mean, that's our paycheck at the end of the day, is being able to answer your questions and you know, doing the best we can within this environment to engage all of you in this work is important to us, right? So here's what we did. So in this breast cancer malignancy and causality classifier, we were able to take open source data from UCI, walk through the process of identifying the 31 variables, targeting and determining of all those variables, which ones were causal to the malignancy or benignness of a diagnosed cell. From there, we found 4 or 5 causal characteristics. No new science in there, just an application of causality. And then we went off and built a classifier. Now with that classifier, that's a digital surrogate. By controlling those parameters, we can control the output of the work. So what we're going to do now is we're going to move into the next phase where you actually get a chance to do this work yourself. We broke it into those same two components. Arnie's going to walk you through in a very similar way an opportunity to do causality work first and then modeling second around a student performance study that was done in South America. Again, this is with UCI data. This work was done some time ago, 2014. It was a study of a school system that dealt with that had 649 attendees, measured around 33 different parameters as a function of grades. Right. So think about this. This is very relevant today, actually, within the coronavirus space. I think a lot of us, I think a lot of us are not wanting to think about what the life was before the coronavirus, but as we go through the coronavirus and we see the potential impact that it is having, the lack of in-person attendance in school, the lack of social contact, how does all that play in the overall performance of students in courses? Well, here is an example of something that was done years ago that we can use as a framework for assessing similar characteristics. And so what they did, they went off and they over 3 semesters collected this data, and you can see here it outlined. It collected whether the student was male or female, the age of the student, what school they were in. These were 2 different school systems, right? What address, and you start to get into some very interesting parameters that were collected. We're going to talk a little bit about this as well, which is, why do you collect certain parameters in a world today where some of these things shouldn't be used in terms of determining outcome? You do it to determine if there are biases, for example. We get into mothers, were the parents cohabitating, right? Were mother and father together or weren't they together? What was the father's education? I like some of these way at the bottom down here. Workday alcohol consumption. Was there workday alcohol consumption? Was there weekend alcohol consumption, right? What was the health status? Was there internet accessibility at home or not, right? All these parameters were collected. And what we're going to do now, what you're going to do now is you're going to take this data, bring it into our ecosystem, and we're going to first figure out, of all this data, what's causal to your grades, at the very bottom here, G1, G2, 3. As a sidebar, we're also going to say, is there anything causal to absentees? Does anything cause a student to be more absent than another? And that's the very first piece of this exercise, right? So I'm going to turn this back over to Arnie. Arnie's going to bring you back into this ecosystem. He's going to walk you through. Is this done yet?
No, it would take a while.
Okay,
so
so let's go back into our causal world, bring in the data, and start to walk through this space.
All right. So let's go back into. So we were here. And if you kind of closed any of the tabs, no worries. We'll just go into our notebook over here, and we can go into the editor and then select the Jupyter Lab. I didn't close mine, so I have mine up and running here. Let's go ahead and bring up the part A. So now that we have your guys' notebook, we already have installed the CausalNext and the pie chart, so we don't have to do that again. Let's import the necessary libraries like we did, like you guys saw, like we did with the breast cancer data set. Again, setting up some data here. And now let's take a look at the data set that we have. So we're going to look at the student performance. And for some information that Dr. Jerry had, I put them in here as well. So here are the features that we have. And then if you want more description on what are those, what those features are actually mean, they're going to be listed in here. So let's go ahead and dive right into it. One of the things in this data set here is that, and it could be a sensitive topic, but in some case, you might want to remove data based on some sensitive content. So for the demonstration purpose, we're going to remove some of these columns out of this data set. Not because it's just for demonstration that you can remove it and it will kind of change the behavior of the causal model, but you don't have to remove them if you don't want to. But we're going to remove kind of what school they went to, the gender, age, and so forth. So now that we have removed some of the sensitive columns, we can see the data set again here. And in this data set here, what we're interested in seeing, eventually we want to get to, is looking at the G1, which is a semester 1 grades. And they go, I believe, range from 1 to 20, I think it was. We need to do the same label encoding like we did previously in the breast cancer data set. So again, now we have a lot more categorical features. For example, address, P status, school supplement, and so forth. So let's go ahead and apply some transformation. So what we did is that we took every column. It tries to find where are the text-based or text values, and then get those columns and convert them to a numeric. So we'll apply, if it's a binary one, it will apply 0 and 1, and then continue to add value to the different variables or different categories. So now that we've converted everything to numerical values, CausalNext is able to process this. And like we talked about in the past, what I said before was that there's 2-step process for the causal analysis. We want to create the structure, and then we apply conditional probability to the structure. So this will take some time. So hopefully our predictive model is going to be close to ready, and then we can look at that while we wait for this to kind of simmer through. So right now it is computing the structure between each feature. So in this data set, we are not applying any target. So there's different ways to use CausalNext. You can either have a target, or we can go blindly into a data set and just look at, without any influence to the data, of finding causal relationship. So right now we're just looking at this blindly. We don't know what are the causal relationship among these features. Kind of tell us what you can see. And so that's what we're trying to do here. So while we wait on this, I'm going to take a peek at our designer, see what the progress is here. It is still training, so we might have to kind of just get a glimpse at where we're at. Yeah, so we're still just processing through our data here. So it's still just selecting the columns. It already took the parameters from the predictive model, and then it's going to go through splitting the data and then training. So this will continue to take some time. If you're welcome to play with the lab more, you have, I think, almost 24 hours to use the lab. So a wise thing would be to go into the compute, and then maybe select a new cluster and pick a beefier one that is able to run maybe a lot faster. Let's go ahead and take a look at our Jupyter Lab, see where we're at here. So we're still waiting on the CausalNext to compute the structure. This could take a minute or two.
Yeah, which is always a fun piece about all of this. So one of the things that you can do while you're waiting for these causal computing environments to do their thing is to ask yourself, what do you think is going to happen, right? That sort of intuitive knowledge you have. Like, for example, let's think about grades, right? So we have all these grades that are in there, grades G1, G2, and G3. Do we think that the third term grade is contingent on the second, G2, or even G2 contingent on the third? Do we think that? I think that's reasonable to assume. So we should probably expect to see something like that in our causal model. What about areas like in absenteeism? right? If we mentioned before that we were going to take a look at absentee rates in there. Do we think daily or weekend alcohol consumption is going to have an input on absentee rates? I would think so, right, in that particular place. But what about other areas? So, for example, what impact does parents' cohabitation, what impact will that have on grades? What about whether or not a student has internet access in the home or not? So in the world of causality, we often will do an explicit knowledge dump, right? Grab a virtual piece of paper, real piece of paper, draw a circle, right? In a circle, draw all the variables from sex, age, schools, address, right? In a circle. And then in your mind, ask the question, what does this variable probably have in relationship to the others? And do that knowledge dump on yourself, so that when we see a model come forward, you'll be able to compare what it has computed with what your interpretation is, right? The real science comes when we get unexpected results. Remember, human beings are a very interesting cognitive species. And that is, I don't know if you've ever studied the fallacy of failing, or the gambler's fallacy, which is most gamblers can always remember all their wins, but can hardly remember their losses. So, people who are addicted to gambling will tell you that they win a lot, right? They always win, but they can never tell you about their losses. And that has to do with the way the brain operates in that space. So when we go into a project and we're working with our customers, and again, I'm waiting for our compute environment. Oh, by the way, to answer the question, Arnie, yes, the next time we put in the quantum computer for this.
I know.
In that space. So as we go in and work with our customers, and our customer says, oh, yeah, we don't need to do any of this because we are experts in this. Well, they certainly are experts, but that doesn't mean that cognitively they have the right answer. That's in this space, right? So, and one of the activities that I'd ask you to do right now is to think about some of those things, right? What should affect absenteeism? What should affect the grades in those areas? Just mentally think through that very, very quickly as we're waiting for this compute environment to do its thing. There's another point to this as well. Did the other one finish?
It looks like we're into a rough start. I mean, we started with a notebook, and it looks like everything is running kind of slow for us. But here we go.
There we go.
All right, so we computed the structure. So let's go ahead and visualize this structure.
Oh, I remember these, all those wonderful lines. That tells us everything right there. We can stop now.
So as Dr. Jerry explained last time,
this is, as we say, this is grandma's ball of yarn, right? Lots of different threads to pull on here. None of it's meaningful. Let's get rid of the low-hanging fruit that we don't really care about.
All right. Nice. So Dr. Jerry, you talked about, well, let me first give a kind of glimpse overview of the whole thing, and then let's take a look at one of the things that you mentioned, the grades here. Oh, you mentioned, what do people think about, will grade 1 influence grade 2 and so forth?
Gee, I guess if you're getting bad grades in grade 1, you should probably expect to get bad grades in 2 and 3, right? Or a better way to look at this, so that's forward looking. If you got bad grades in G3, the chances are that you probably got bad grades in G2, and the chances are you had bad grades in G1. So that's why it's important to hop on that right away. What about absentees? Are they in here as well? Or absentees? Yep. Where was the absent?
Right here.
Oh, nice.
And look at this one here, the one you talked about, the daily. Oh, was it daily or?
No, the alcohol stuff was WALC and DALC weekly. And so if you scroll around, go back to there you go. So daily alcohol consumption. leads to weekly alcohol or weekend alcohol consumption, which leads to higher rates of absences, right? Go figure. Right? That's probably a lot like my college
and
terms.
Then,
so
interesting one here, romantics.
Oh,
Getting a new girlfriend.
Romantic relationship as a young person, the chances of you being absent from school are pretty high. So here's the interesting thing about this right now is you can take a small pause and think about, well, why is this important? Because this leads us to sociological group conversations and psychological individual conversations that we can have with policymakers, right? We now know that and we'll get back to grades in just a second, we know if we want to improve our absentee rates within the school systems, that is, reduce them, that we can actually sit down with folks and say, well, what can we do to do a better job? Well, maybe, obviously, there are some drinking issues going on. We can put in more programs in there. We can deal with helping young people better understand the impact that complex emotional relationships have on their brain, which in turn have on their desire to attend school. So those conversations, we can now sit down with policymakers, with sociologists and sociologists, group thinkers, psychologists, individual thinkers, and help them put in place programs. But now if we scroll down here to the grades, what are the things that affect grades, right?
Yep.
We have a lot of things that affect grades. And for my poor eyes, we have, what are some of the ones that are in there?
P status.
The parental status, right?
Yep.
So get in the P status, parents' cohabitation status, living together or not. Well, that's interesting. Are we going to go to a school and demand that all the parents live together? No, not necessarily. But here's the thing. We did a study in Philadelphia, for example, years ago. It must have been at least 20 years ago now, where we were taking a look at why students were having such a hard time at school in the inner city school system. Well, as it turns out, those students, if you went back to the home, came from homes that didn't have multiple parents in the home. That's number one. And number two, the individual parent that was in the home had a low level of education themselves. And so what did we end up doing? We ended up so if your mom or dad doesn't know how to read, it's really, really hard to sit down and teach your children how to read, right? So one of the things that we did, well, while children were in school, we actually taught the parent, the guardian, how to read themselves, how to do math themselves. And not only did that raise them out of poverty, but that also created a stronger relationship with the child in that case. That all comes from studies like this, right? Pretty cool stuff. You can spend like 2 years on just this data alone and grabbing sociologists and psychologists saying, what can we do? How many of the people within our community is being affected by this sort of stuff? And then putting in place programs that are out there, right? Pretty cool. I hope you think it's cool. I think it's really cool. What other attributes?
Yeah, so we got higher and then study time.
Higher, yeah. So this is higher is just an attribution that says wants to take higher education, right? Person wants to take it or not. So the fact that somebody has a desire, has a higher aspiration to seek higher, often improves the grade levels. So going back to what could we do to improve first term grade levels is we can early intervene in on helping students understand the importance of it and helping them create a stronger desire to want to do this, right? What was the other one in there? What was the one?
Yeah, well, the higher one also influences the study time. So it makes sense that he's has desire to do it and then wants to study longer. And which influences
study times have an impact on grades. Our children would say, no, they don't. We don't need to study more. Well, actually, you can turn around and say, I just did a study here, and the answer is yes, right? So wanting to do more impacts your doing more impacts. And by the way, this is a really interesting triangle, right? So this is what we would, and I think this is one of the things that Artie's trying to point out here. This is a cofactor, right? This is a confounder, I should say, a confounder in this space where oftentimes the real impact is study time on G1. But when we look at that, we also see that the study time impacting G1 is also impacted by a desire, right? So our goal here is to how do you deconfound this, right? Because this is a classic example of X does Y, but Z also does X and Z also does Y. So that's, you know, study time impacts grades, but there's something that impacts study time, and that same something impacts grades. So we have to deconfound this particular triangle. So we look for these triangles in our areas, and so that we can pull them out. And a lot of time what you'll hear social scientists saying is, I've deconfounded our model. I've for example, binned out folks that have no desire versus folks that have high desire. So you'll actually create two models. You'll compare and contrast all those that have low desires to study, and you compare the results of that relationship as compared to those who have high desires. Well, we don't worry about that here, right? Because now we're at the true cut. Once you start deconfounding models, you actually remove a lot of the nuances in your model space. So we actually look for these as an opportunity to get higher fidelity policies out of our programs. Pretty cool stuff. Pretty cool stuff. All right. So what do we do with this, Arnie?
Yeah, so the next step is to, again, take a look at our structure here. We have some, we applied the threshold, and which will leave us with some of the features here that are just not as causally as strong as the kind of these inner connectors. So what we need to do is remove these extra features here, because we only want to have this one causally connected structure. So we go here and we get the largest subgraph, plot it again, and it's gonna just take those this inner structure. So that's what we see here. So it looks slightly different, but it is all the same connectors, all the same parameters. The structure just tries to balance itself out to be not like on top of each other and so forth. So meaningfully, it is the same structure. The next step is to use this structure here and apply a conditional probability on this structure. So we're going to tell our Bayesian network, here's our structure, use it for our Bayesian network. So we're going to apply we're going to take our processed data. So we already have our data now been processed, or we only use conditional or continuous variables, sorry. When we use the Bayesian network or apply conditional probabilities, that model does not care about only the causal next with a structure needs to have numerical values only. Like I said, when we did the breast cancer one, it is very important that we discretize our data, because otherwise it will take us a long time, or our memory will blow up. So what we need to do is take some of these variables that are continuous variables, and we want to turn them into categorical value. So that's what we're going to apply here. Let's look at the process data again. So we apply some study time here. We just, instead of being 1, 2, 3 or something like that, we apply short study time, long study time, for example. We have some failures, there were some from 0 to some values. Now we just have failures or no failures. And then also we just simplified our grading system to be either pass or fail grade. So this will help us apply the conditional probability. So now that we've applied or discretized our data, we need to split our data set into test and train. So again, we did this. Now we're doing it programmatically. We did it also in the designer. Here we're going to use a 75% split for the training set. And then let's go ahead and fit this data. So now that we've done fitting the data, we can take a look at some of the results. And let's take a look at here briefly. And we can see how the conditional probabilities is applied to the grade 1 and to the rest of the features. We're not going to dwell on this. you can study this as you want. What we want to do next is to create a predictive model. So let's go ahead and do that. I also put in here extra note in here if you wanted to take this model out of here. We can take this model and we can use the Azure data store, and we can kind of create a data store in there called student performance, or we can just upload our student performance in there. We can do both ways, so let's go ahead and do that. So I'm going to take again, when we go to the graph, we're going to only look at what are the causal features to the grade. So it's going to take a look at those features and pull them out. So it's the address, P status, study time, failures, school support, and so forth. We're going to also add our target into this list. We're going to create a CSV file that we put in here. Then we're going to pull in some Python Azure ML SDK. So this is how we use Python to communicate with our Azure. What we need here is that we need to grab some information from our lab. So going back to the original lab setup, they provided us with a whole bunch of information, and there are some things that we need. We need the resource group name. So let's go ahead and get that. So we need the workspace name, a resource group, and subscription. So let's go resource group name here, copy that. Paste it in there. We need the name for the workspace. I think that's Azure ML workspace name. That's this one here. And then we need our subscription ID. So let's get that one at the top here. Copy that one. So fairly simple once you know all the commands. So this is gonna tell the notebook, oh, you are Arnie. Yeah, you already have a workspace. Let me pull that for you. So workspace name is not defined. Let's find out what we copied wrong here. Did we not copy that right? So it could be that it should be all correct. So we'll have to dig into that one, but it should be enough to, oh, the workspace. Oh, I'm sorry, I did not run this import here, so apologize. So now that we have workspace imported, this method, let's go and import it. So now it knows, okay, Arnie, you have this workspace. I see it from your subscription ID workspace, etc. We're gonna get a default data store. All right, we got that one. So that's our data store that we have in here. So this one here. And then we're gonna say, take the file we just created, the data.csv, and create a new, register a new data set called student performance, and we'll do that right away. So it's going to pull this data, it's going to register this data set, and then now we're done. So going back into Azure Machine Learning Studio, we should see now 2 data sets. And here we are.
Look at that.
So that was a way, or I showcased now how you can use the notebook to kind of pull things in. And we also had gone through the step of just doing it manually by uploading the file. So there's multiple ways to deal with Azure Machine Learning Studio. Yeah, they know how to do this well. So let's go and jump into the designer and create a new new ML exercise. So again, let's use our cluster that we did that was already created. We're going to now bring in the student performance one. So while we kind of set up this, I bet you're interested in knowing if the other one was completed. Let's take a.
I would be.
We're still processing. It's getting. We finished the training. We're just getting the scoring done. Should be done soon. So let's go ahead and go back to the designer and work on our current data set here. So again, you can right click and we can visualize our data. So let's see what we just imported from our Jupyter notebook. So here we have it. We have 395 rows. We have the 8 columns, including the target. We see the distribution, and this is our data set we're going to work with. So these are, again, now we're going to create a digital surrogate because we only have causal features to grade. And like we did before, let's go and select. Well, technically, we don't need to select columns because we just brought in our data set. But in demonstrating, if we had brought in the whole student data set, we would go in here, we could select the data set that was that we needed. But since we already have a data set we have everything in place, we don't even need to select the columns in here. So, but there's a processing step we have to do now to change our grades from continuous variable to categorical. So to do this visually, we can do it using our group data into bins. So in here, we can have a 0, 10, 20, for example. And it's going to take a look at the data. Connect the data here. For some reason, it's not letting me connect it.
Well, if we go back to.
Go ahead, Dr. Jerry.
Go back to the old school of importing all the data and then select.
Yeah, let's go ahead and do the old school. It could be that I didn't specify it as being a tabular data. Oh. So apologize that I think that's what's causing it. Because
this is why salespeople never do real live demos.
Because it says here any file, so I did not register as being a tabular data. Okay. So apologize. Let's go ahead and just upload this data.
Yeah. One more time with feeling. That was planned.
Of course. So let's go ahead and get the student performance. Going to parse the data. We're going to apply headers. We got some headers in there.
There we go.
Excellent. Then we accept the schema. It's pretty good about predicting the schema, so we'll just keep going. And now we got the 3 student performance data sets in here. So going back in here, let's just swap out this data set. And now let's go and select our columns, like our original plan. Now we got to go and add those columns in there. So we need address, P status. We need our grades. We need study time failures. And we need school support, family support. And higher, desire for higher education. All right, now we got every column that we need selected. We go and do our grouping of the bins. So select G1. So now we're gonna take the grading column, and we're gonna look through the data, and if there's values between 0 and 10, we'll apply that as being a 0, and then, or sorry, I think it starts at 1. So it will be given the value 1, and if there's a values between 10, greater than 10 and 20, that will be given the value of 2. So that's kind of how we categorize our data. So now that we have this in place, we can go and split our data set, just like what we did in the other data set. So again, yeah, the grouping will be in here. You get the quantized data set, and then you can also get some transformation information here. But we're gonna want to just get the already transformed. We're going to split the data into 70%, 30%. Let's go ahead and get the model, train the model. Let's go ahead and apply some machine learning to class boosted decision tree.
By the way, just going back to that 70-30, we often blow through that number, right? As it's sort of like scientific truth that it's always 70-30. I always encourage people who are new to machine learning, building models like this, to spend, once you get all this set up, is to spend the time and take a look at the performance characteristics of your model, right? How much is it either overfit or underfit? False, true positives, true negatives, false positives, false negatives, right? And what you can do in this case is set up a small side experiment, and that is go back and shift it 25% development and 75% test, and 50-50 and 75-20, and and then plot the results out. And I think you'll see some interesting results, and it's worth the time if you're new to this and you're programmatically just entering 70% development, 30% test, to actually ask the question, does it have an impact on my model, right? If I did 10% development and 70% test, does that have any material impact? And the answer should be yes, right? And then as you go through, you can then begin to tune the performance of your models specific to your model's needs, rather than just accept the rule of thumb of 70-30 or 80-20, right? And you can do that easily in here now, right? Now that everything's set up.
Yeah.
Yeah.
And another, just to complicate it even more, we can split this data again. So let's say we took 60% and then we took the 40% and split that again into 20 and 20, or 30 and 10. And then we can use something like tune hyperparameters.
Yeah.
And then in there, we can then start, okay, let's take some of the testing data and And we split the training set into K clusters, and then, but we also want to validate each cluster with some test data. So we use maybe, I don't know, 10% of it, or to actually validate each cluster, and it tries to tune the parameters of the model. So meaning in the model here, when we select these values, we don't have to select a fixed amount. We can go and select a range. So you can put in whatever range. It's going to go and try out every combination of these parameters, and it's going to just try to find out what's the best parameter tune for this data. So that's another neat feature that Microsoft has set up in this a really easy and visual pleasing way. So again, we've took the data, we selected only the causal features, so we got a digital surrogate model. We had to convert our grades into pass and fail. We split the data into test and training. We have models ready to go. We train the models. We score the model to get the probability and the labels for both the training set and the test set. And then we're going to evaluate the results of both models. So let's go ahead and just submit this, create a new one, experiment 2, and hit run. So this will take quite a long time, I think. I don't know if we'll have time to go see the results, but at least you have seen how you set it up. But at least we can go ahead and go back to our other data set and see where we are with our modeling. We're on the last step. Dr. Jerry, what do we want to jump into some slides and then take a breather in between, and then we can kind of look at the data?
Well, let's go into the slides real quick here. Let me just grab the slides, send over live. And we'll talk about some of the stuff, and we'll finish up a little bit early today since there's not a lot of questions coming through in this area here. So let's think about what we've done, right? We were approached by our business partners in higher education field, and we were asked the question, hey, you know, we'd like to better predict, you know, how students are going to perform within each semester in terms of their grade. And of course, we asked the question, well, why is that important to you, right? They said, well, we're interested in identifying new programs. And we said, well, why is that important for you? Because we want to actually improve the lives of our students, right? We eventually ask enough why questions, and we get to the spot where we realize that what can we do? We can actually put them in the position of changing tomorrow, just not observing it. That's the important part of this process. Remember that cycle of life, right? Step number 1, data is because of us, not in spite of us, right? Data is the debris of human activity, right? So we collected a lot of data associated with characteristics of our educational process. We then sat down, and as Arnie showed you, we went through and developed this causal model, right? Which is, by the way, science. I mean, this model that we're seeing here is science. We actually can show, not just predict between causal and correlations, we're actually showing what is causal to the grades now. That's real science. So you were part of a science day here on AgileThought. And by the way, we're going to be posting this later on to LinkedIn. So if you want to contribute to that conversation, please do so. So we figured out, hey, grades, there are certain characteristics of it. Parental statuses was in there. Study time was in there. We also identified our second goal, right? In addition to the grades, absentees, right? It'd be great to have students in class all the time. Turned out that we found a lot of characteristics are associated with absentees. So we did that, right? And you can see here that some are stronger than others. Some are weaker associations in here. If we take a look, we see some confounders as well as in this space, which is fairly interesting. So there's a lot of science in this causal graph itself. From there, our sociologists and psychologists said, hey, it would be really good if we can develop a digital surrogate so we can control the prediction. So can you build a predictor model for us based on these causal inputs, so that if we can then take the third step, which we're going to talk about here in a second as our machines are computing in the background, so we can then optimize the results. And we did that. We went into Microsoft land, Azure ML, we brought in that data set, we created a very simple, straightforward causal AI machine learning model on those inputs. And the question is, what do we do with that? Right, so we're now at that one step. We now have the predictor, right? The causal input predictor digital surrogate. Well, what we want to do with that is, if we go back to our next slide, we talk about optimization now, right? So this is our last subject today. We're not going to do this work. It goes a little bit beyond the capabilities of a sort of an intro level. But if you think about what we have in terms of our digital surrogate, again, digital surrogate, by the way, I hate that expression. I'm trying to break myself of it again. When I say again, a digital surrogate is what? It's a causal predictor. That's all it is. So we take our inputs that are causal, we take our non-inputs that are correlation, we strip out the correlation. I want to put a plug here for correlated inputs. If your goal is to just identify something accurately, then you don't need to do this work, right? I had a client one time that was in the lab field. What they did is they did lab procedures. You know, if you got your blood drawn, if you had your whooping cough test, if you had skin rashes examined, etc., you would go to the lab, and they would take the lab results, and then based upon your procedures, they would submit your procedures to the insurer, right, for repayment. And one of the things that they noticed in this process was, if they submitted the lab procedures as A, B, and C in the order that they had occurred, there was about a 60% chance that they would be accepted, 40% chance that they would be denied. Think about it. So if they did procedure A, then procedure B, and procedure C, it was about a 60-40 split. On the other hand, if they took those same procedures and did C, B, and A, just reverse order, they did nothing different. They just reversed the order that which they were submitted explanation of benefits to be repaid, they increased the 60% to around 85-90%. That's kind of wacky to begin with, and but it was an observation. And so they asked the question, can you develop a predictor for us, right? That would allow us to predict which sequences, temporal sequences, would be more likely repaid than not. And that work was done. Very successful, by the way. It actually, they took all that data and they were able to predict in excess of like 91-92% which sequencing would be likely to be repaid. Well, here's what they ended up doing then. They ended up taking that and treating it as a causal network and saying, well, we are going to do these sequences. Well, it turned out that that predictor was not a causal predictor. It was a correlation predictor, right? So they were able to observe outputs, but they weren't actually able to change the inputs to create an optimized output. So they got very frustrated in the fact that they had to manually go about doing this. So later on, we actually sat down with them and went back and did the correlation, causation analysis, identified what was causal in that world, and identified the causal components to that, which had to do with other characteristics other than sequence. That actually had to do with textual language that was submitted in the CBA version that was different than the ABC version that nurses and the doctors would read to provide the context through which they were getting repaid. Very, very interesting in that space. So going back to, we have a digital surrogate and we have my predictive outputs. We have several, in our case of education, we had several causal factors going in, some of which were predicting absentee rates and others were predicting grades. The next question is how can we maximize that space, that predictive space, right? Can we multidimensional optimization, right? Can we maximize attendance and maximize grades all at the same time? Well, yeah, that's easy, right? Not easy, it's time and materials. All we have to do is ride the gradient fields of our search space. So in this last area, the prescriptive area, the step right prior to us going into the field and applying our work to the field to see the outcome, our goal is to take all those causal inputs and search that whole space as a function of maximizing the output, right? What combinations of drinking, parental status, internet usage, desires, what combinations of all those will maximize my attendance, maximize my grades in there? And there are a lot of different ways we can do that. Now, unlike causality and unlike developing predictor models, this is an area which is still mostly in the area of science experiments and less so in the areas of engineering work at the scale. So what are some of the methods? We use stochastic methods like Monte Carlo work. That's my favorite, easy to use, right? We actually know the causal inputs, right? We know the distribution characteristics. Where do we know that? Let's go back to our causal analysis, or let's go into our work that we did in Microsoft Azure ML, and we know those characteristics, so we can now generate random inputs based upon those normal distribution, Poisson distribution, whatever distribution characteristics they have, and then identify ones that peak both our two or multiple goal output areas. We can also use population methods such as evolutionary computing, which is my favorite, which is, can we evolve structure out of this? We can do linear and multi-objective constraint-based optimization, and we can use things like particle swarm optimization, right? Which is a classic method in here. By the way, I'm about ready to sneeze on you guys, so if you hear me mute this, that's only because I'm muting muting so you don't hear the sneeze. So the idea here is what? The idea is that we take our digital surrogate and we apply optimization activities against the inputs to maximize our output, right? This is where we now answer the how question, right? So when you have the student school board saying, how do we improve student grades? That's this step. You can't do that step on the previous work, the predictor, and you certainly can't do that step on the causal piece, and you can't do that step just by collecting data. You have to go through an optimization activity to identify how. And once we have that work, right, that work that's coming from step 4, what can we do with it? We can then take the inputs and then ask the two most important people at this phase that should be on your project, that's not on your project, a question. And who are those two people? That's your sociologist and your psychologist, right? So a psychologist is somebody who understands how to change the behavior of a person, and a sociologist is somebody who changes the behavior of group dynamics, right? And again, our goal here is to change tomorrow, not just observe it. So if we're going to change tomorrow, if we're going to change the data that is generated from people, we have to have people who have expertise in changing people, either individually or in group-wise fashion. So we go back to them and we say, hey, psychologist, hey, sociologist, how do we take this element, how do we take drinking? We know drinking now, both daily consumption and weekend consumption, have a direct impact, indirect and direct impact, daily indirect, weekend direct impact on absentee rates of a student. How do we change the behavior of an individual? And how do we change the characteristics within a group on that? And they can sit down and think of all sorts of different programs. And what will we do with that one program alone? We would go implement that in school A. We would not implement it in school B, right? And we would wash, rinse, and repeat this cycle for 3 more terms, and we find out how impactful those programs are based on the causality that we've seen as a result of our work. And therein lies the end of this journey for us. We'll go back and take a look at some of the data that we have in here. But the end of this journey gets us back to where we can now take the results of our work, take them into the field and implement them into the field, and wait for those systems that we've put in place to recollect that data, right? Based upon the changes in behavior of people, right? Because we've now changed policy. We've done something, we've touched an individual. They in turn change their behavior. Their interactions with the systems that we have in place have picked up on that. We have new data that is brought into the system, and what do we start over again? Start with step 1, collect all that data. What do? We ask the question, is this causal? You never know. It could have changed, right? We could have impact. Maybe drinking is no longer a causal input on grades anymore because of the programs we put in place. We then wash, rinse, and repeat this cycle. We are now put into a position of changing tomorrow, not just observing. That should give you a sense of superpower, right? That's a minor superpower that we all have, which is very different than 5 years ago, where we actually spent most of our time just observing tomorrow and not changing it. So if you think about it, you now have an ability to affect outcomes, right? Which is something I want to talk about at the very end of this. Arnie, do we have any results?
Yes, we do. So let me go ahead and
yeah,
try to get your stuff to share. Sorry, it always takes so long because I got one screen going on. Not so fancy as Dr. Jerry with multiple screens. All right, here we go. So now we see our model here is completed. So this is our first model, the breast cancer one. So let's go ahead and take a look at the results. So again, give you a fresh refresher. We took a breast cancer data set. We filtered out only the causal features. We split the data set into test and training. We trained the model on the training set. We scored once the training was completed, we scored the model for each data set, the training data set and the test data set, and then we created some outputs from the results or from the scores. So let's load those in, and here we see the results. So here at the top, since I connected both left side and right side, left is our training set, right side is our test set. So you can just click between those. It's going to show us on this graph both curves. The ports here are switching between the data we see down here. So looking at the data, by default, the thresholding is the probability you want to be for the classification to go being 1 and classification to be 2, meaning malignant or benign. So what we see here for our training set, we only got 1 error. So that is highly likely to be overfitted, and we can see that in our plotting here. The ROC curve is a good way to view it. So you can see that on the test set, which is the green curve, we were definitely not as good performance as our training set, where it's pretty much 100% accuracy. So this is our classical confusion matrix, and you can see also what our accuracy, precision, F1 score, area under curve, etc. You can then click on the right port, and you can see the results on the test set. We got a total of 13 errors or 13 missed labels. Not bad, but still slightly overfitted. So that's why I was talking about why we compare our training and our test set results together, because it's a very important way to check our modeling. So that's where we have the results. So we've gone and we did a causal analysis. We got causal features. We created a digital surrogate model, which is this model that we just created. And now we can turn our optimizer on top of this and optimize certain parameters to get our optimum results.
That is awesome. So let's wrap it up today. We'll return some time to the folks here. Let me just go grab the screen back. There we go. Share that. Share this. And share that. Send live. All right. In summary, today we learned 3 or 4 things. Number 1, we learned a heck of a lot about Microsoft's Azure machine learning environment, right? As a data scientist or machine learning specialist, we learned that how to bring in data, how to visually program, and how to produce results, right? We also learned to use as maximize your compute space as possible if you don't want to be waiting around a lot. That's an Arnie and Dr. Jerry issue for the next time, which is we've proven that when you run on one CPU, there is a direct correlation between the amount of compute time and the amount of compute resources. So that's been reproven. The second piece we've done is we've learned a little bit about a different way of looking at the life cycle of AI, right? We've learned that data begets analytics, and analytics, the data science. What's the data science piece? The causality piece, understanding the relationship. Data science is understanding the relationship of data. That's all it is. It's data science, right? Understanding the relationship in data. One of the most important pieces of information we can get, besides the distributed characteristics of data, is their relationship to each other, right? So we did that with our causality work. You had a chance to see how CausalNext is an important open source tool that can be used. And there's several other tools that we can use in this space, but it is an important one. The second thing we did was, now that we know the causal inputs, we learned a lot about how to build a simple model, predictor model based on those causal inputs. And now you're in the world of digital surrogates. And then we talked a bit about how to use optimization routines to prescribe the inputs needed to achieve the benefits you want on the output: lower absentees, higher rates of education, right? And those prescriptions are then often implemented in the field. If you don't, by the way, here's a little plug, if you don't implement them, nothing's going to change. And that's a key thing here, right? Our goal is what? Our goal is to change tomorrow, not observe it. So a question you always want to begin to address with your business partners is, when we come up with a prescriptor, a change, a recommendation, can we go implement them? If the answer is no, then why are we doing this? Right? If the answer is all we want to do is observe tomorrow, I think that's a little unfair to the people who can achieve the benefits from the work that we're doing. So we go implement them. We sit back, we let a day, a week, month, a year go by, and we recollect data. Now let me put a little plug in there on how much time, which we didn't talk about in the optimization, but this is a really good time to talk about. There's a theory that was developed in electrical engineering around how fast do you need to sample audio information in order to reproduce it at a high fidelity. Now, for most of us here, those kind of conversations have long since gone, but there was a time when we used to buy high fidelity stereo systems, right? And these were stereo systems that sample that audio at such a high rate that when you then put it into analog to digital, did all of its stuff, and then digital back to analog, you could hardly tell the difference, right? It was high fidelity. And that theory says if you want to sample at a high enough rate, it's called the Nyquist Theory. And Nyquist said that in order to reproduce the underlying frequency to the extent that it looks like the original, you want to sample at least twice the rate of the underlying. So if you wanted to hear 10 kilohertz of signal, you would sample at 20 kilohertz, right? Well, we've applied Nyquist theory now to information theory as well, right? The modern day equivalent is in decision theory. So if somebody comes along and says, hey, I want to make a decision every week, right? Well, how often would we have to sample our information and come up with subsamples of decisions? Well, twice a week, right? If you want to make a high fidelity decision on a weekly basis, you have to reevaluate everything at least twice a week. Well, twice a week, Monday, Wednesday, well, that doesn't make sense. So why don't we just do it every day? So if you're on a weekly schedule, you want to do this process daily. If you're on a monthly schedule, again, twice a month. Well, why twice a month? We'll do it once a week. If you're on an annual basis, rather than twice a year, we do it every quarter, right? You see the point here, right? That what we're doing is we're doubling the rate at which the decisions are needed in order to provide high fidelity recommendations to the people making those decisions. So if we're going out and trying to make decisions every term around education, every 3 months, we want to reevaluate this process at least monthly, right? Twice a month or twice in a term. But if you do it on a calendar basis, on a monthly basis, that gives you 3 times within a term. Pretty cool stuff, right? So Now we've implemented those. We sit back and wait for the respective period of time. We collect new information. We walk through the process, wash, rinse, and repeat. We're running at twice the decision rate at least of our decision makers. We're supporting them with social and psychological sciences. They put programs in place there. We see people's behaviors change. We collect new information, wash, rinse, and repeat. We are changing tomorrow, not just observing it. Very, very important. All right. So where do we go from here? Well, you have superpowers now, and I would hope that you would go out and use them for good in the world and actually make the world change rather than observe it. So the very first thing we want you to do is we'd love to get feedback from you on how we can improve this process. This is a labor of love for us, so we love doing this work, and we're always looking to improve it. So anything we can do to improve this work empowers us to do more of it and get in front of you guys more. And we'd love to hear. So please send us an email, send us feedback on that, and if, you know, good or bad, we have thick skin and all this sort of stuff. Just make it, you know, critical feedback that'll help advance the cause. The second is feed forward. This is us to you. We'd like to hear, you know, about how you think you can apply this in your world, right? Email me. If you want to just spend 20 minutes with me and just say, hey, Dr. Jerry, I have this idea on how I can apply it to, you name something. Name a financial problem, name a healthcare problem, name an insurance problem, name a retail problem, right? I want to reduce spoilage in my company's apples and banana products. I want to reduce fraud. How would I apply it? Email me, jerry.smith@agilethought.com, jerry.smith@agilethought.com. Just email me. I'll spend 20 minutes with you, right? And by the way, I will not turn my salespeople loose on you. This is you and I talking, right? As two professional people, this is you saying, I got an idea, doesn't make sense. At some point down the road, if you choose to engage in a sales cycle, that'll be a different conversation. But for right now, I would encourage you to take me up on it. Reach out to me, give me a call, send me an email. We'll schedule some time to get that going. The last area, so that's you and I again. The last area is in the area of upcoming events. As soon as I can get my there we go. We just completed our Accelerate event, and that was so much fun. That was a day's worth of activities. More people than I can count on this one. And we have those recordings available to you. I was on a panel with some folks. A lot of people were on talking about different areas. I'd encourage you to get in there and look at it. Here's a link to that Accelerate on Demand capabilities. Oh, there we go. Addison posted it for you. In addition to that, we have some analytics in a day coming. You won't hear me. You'll hear one of my associates, Jose Gincilla. He'll be on talking about how to do analytics in a day, the process of data engineering, bringing into analytical capabilities of Power BI. So if that area interests you, I'd encourage you to work in that space. Arnie, do you have any last thoughts before I summarize, wrap it up, and then turn everybody loose?
No, I think if people people that are still attending could throw us some questions, we'll be happy to answer some of the last questions if somebody has any. But other than that, well, yeah, just otherwise they can reach out to us.
I do like DK. I'm laughing here because I just got over and started scrolling through. Yes, we should use the quantum service from Azure. We're definitely going to practice on that one for a little bit of time, right? That's a good one. Oh, but a little sidebar, since we have a little bit of time. Evolutionary computing, you know, in terms of the prescriptive side, right? Prescriptive step, where we're trying to maximize inputs and outputs, maximize the outputs based on the inputs. When you use evolutionary computing, when you use that approach to search through that search space, that is a functional quantum computer, because evolutionary computing will find holds every possible state in that space at once, and it's Schrodinger's cat all over again, right? We neither know whether the cat is alive nor dead until you open the box and secure the state, right? It's both alive and dead, actually, at the end of the day. And in evolutionary computing, as a method of optimally searching an entire multidimensional search space, that evolutionary computing capability actually holds all states possible until that state is tested against its goal. It's a functional quantum computer, right? Pretty cool, pretty cool. So evolutionary, I put a little plug there for evolutionary computing. All right, with that said then, I will just close out here by saying, change tomorrow and don't observe it, right? If there's one thing I'd like you all to do is just go out there and change tomorrow, right? Don't be a passive observer of the world go by. Be an active participant in it and use this superpower to actually change tomorrow. If you want more motivational speeches like this, reach out to me, jerry.smith at AgileThought.com. I'll be more than happy to sit down and think through your space with you and hear the journey that you're going down. Between Arnie and I, will get that done. With that, if there are no more questions, I really appreciate it. And thank you, everybody, for joining in this next iteration of AI in a Day. And we hope you have a productive day and future ahead of you. Bye-bye all.